Thank you, Chairman. Thank you. So my name is Takeshi Iwashita. I am from Kyoto University. And today's my talk consists of three parts. First, I will introduce the research activity of RIKEN application group. And next, I will state personal opinion for next generation systems and applications. And finally, I will introduce my research about the linear iterative solver for accelerators. Yes, so application group consists of 12 subgroups, and these subgroups are categorized into two parts. And a pure application group consists of 8 these subgroups, and also the computational science group consists of these 4 groups. And the computational science group will help the activity of pure application group subgroups. And the application group is led by 4 co-leaders, me and Professor Shimokawabe, Professor Takahashi, and Professor Fukazawa. So here I would like to introduce briefly the topic of the pure application subgroups. In the life science subgroup, so they consider the multi-layered complex phenomena from the atomic level to the level of cells and organs and individuals. And in the new materials and energy subgroup, so for example, they solve the electronic Schrödinger equation given the positions of the nuclei and the number of electrons to predict electronic properties of the various materials. In the fundamental science subgroup, they focus on the particle physics, nuclear physics, and space and planetary fields. And in the social science subgroup, so they mainly focus on the automobile system, and they try to predict the automobile and the pedestrian traffic volumes. In the weather and climate subgroup, so they consider various weather and climate models for predicting meteorological phenomena, climate, and even the Earth system. And in the earthquake and tsunami disaster prevention subgroup, so they consider various science and disaster prevention methods related to the earthquakes and tsunamis. And in the manufacturing subgroup, so they consider various numerical approaches for designing and evaluating physical things, so goods and tools. And the last one is a digital twin and society 5.0 subgroup. So the target is relatively new. So they consider integrating cyber space and physical space. So I'm sorry, this is very brief introduction, but so these are the 12 pure application subgroups. So this slide shows the result of activities of the application research group. So, and each subgroup already conducted a survey of the current status of each application field, so mainly last year. And then, so they investigated the achievements expected in each application area around 2030. So, and it involves the investigation of the features of the next generation computing system which are necessary for achieving the goal. And also it involves some survey of parameters of the system architectures. For example, computational performance, memory amount and bandwidth, and inter-node communication performance. And each application subgroup also consider the programming models, for example, language, compiler tools, and libraries and the frameworks. So they, they analyze their necessity for these kind of things. After that, each application subgroup constructed a benchmark set that reflects the characteristics of typical applications in each area. So this is still ongoing part, but the developed benchmarks were already provided to the architecture research group and the system software and library research group. And each application subgroup had already hearing by the architecture group members in last June and July. And these benchmarks are used for evaluating the future devices and system architectures in vendors. it's ongoing. Next, I would like to show you slides provided from the 3 subgroups. So if you are interested in other subgroups, so maybe after this symposium, so we will post the slide to the symposium website, so please refer to that. So this is the life science group's result, and they expect in 2030 multi-scale simulation from the molecular level to the organ and the human body level. And also they expect the integration of the multi-level data and the simulations of biological phenomena with AI and LLM. So they are their expectations. To achieve this goal, so they demand a speed up of individual applications, of course, and also they demand a combination of different type of applications. So this slide provided by the Weather and the Climate Science group, and they expect that a realistic and detailed weather prediction system will be developed in 2030. And also, they want to realize sophisticated Earth system models that qualitatively improve the understanding and the prediction of the climate change, so big scale. And also, a comprehensive understanding of multi-scale phenomena from microscopic to planetary scales will be expected in 2030. This is the Weather and Climate Science subgroup expectation. So to achieve this goal, so they demand the dozen of times faster than Fugaku's system and in effective performance of overall workflow. And also they pointed out heavy costs spent for the source code refactoring to use accelerators and major modification of algorithms to fully exploit the benefit of the new system. Next, this is a slide from the social science subgroup. So, and this group focuses on automobile system, and they expect extreme disaster or spontaneous disruption events can be extracted from the large number of simulation results in 2030. And to achieve this goal, they pointed out the demand of the many high-performance cores, and also they want to solve the many multiple scenarios to achieve this goal. So this is a demand from the social science subgroup. Next, so I would like to show you a plan for 2024. So in 2024, architecture research group will determine some future direction for the next system. And following this decision, so the application research group will conduct their investigation. So one of the important things is to modify of the science roadmap of each subgroup. And then, so they will investigate a new algorithm or implementation method to fully utilize the next generation computing system. So if architecture is determined, so maybe each application subgroup will try to develop a new things, new algorithm or new implementation methods. So, and maybe they will consider efficient use of accelerators. Okay, so from that, I would like to show you a personal opinion. It is a personal opinion. It is not directly related to RIKEN. Please be careful. Okay. So I would say, first I would say about recent AI technology. So recent AI technology is really amazing. But computers have done amazing things for many years. Computer has worked much more efficiently than the human in some areas, especially conventional simulation areas and HPC areas. For example, a human cannot do even 10 arithmetic operations in a second. So, and the computers give a very accurate analysis result. And the recent AI technology, it's amazing. It can work in the areas that we thought human could do better than computers. For example, judgment, prediction, estimation, even in generation process of some new things. So even in these areas, so AI technology can work very well. So this is really amazing. But it cannot cover all conventional simulation areas from the viewpoint of accuracy. So, and I would say, so in Japanese idiom, 適材適所. So this 適材適所is very, very important. So English translation, it means right people, right place. So both conventional computational science and AI and ML approaches are both important. And I hope human beings can contribute to the next generation applications or systems, hopefully. Finally, I will say, so right computer, right AI, right people, all right place. I think it's very important for the next generation applications and systems. So, and this slide shows the application area supported by the next generation computing system. So currently, maybe we have two major classes, so conventional computer science and AI ML workloads. And also, AI for science is becoming very important now. But we have to consider that these two classes have different characteristics. For example, in this area, so computational computer science area, so the program is usually it is high byte per flop ratio. For example, space matrix computation or stencil computations are often used in these workloads. In other hands, so AI ML workloads, so the program is usually the low byte BF ratio. And in other words, it is computational intensive. So, and for example, matrix product, especially many and small and dense matrix product often used in these workloads. So I think the next generation system have to support these two workloads, so not the only one. So this is my opinion. And also, we have another class of problems here. So this is a huge optimization problem. In this case, byte per flop ratio is very, very low, but the huge computational effort is demanded. And I think this type of problem can be solved efficiently by the quantum computing system. So, and a new system consider two major parts, and also, how to say, a little bit care about the future direction of the quantum computing device. This is my opinion. Okay. So, and what should we do from the viewpoint of next generation architectures? So I think the accelerators, including some special instructions of the CPUs, are essential for improvement in the system and the node performance, especially performance per watt. So therefore, we should consider effective use of accelerators. And now the most popular accelerators is the GPU. So here, I consider using GPU. In this case, GPUs have higher performance in low precision arithmetic than in 64-bit floating point arithmetic. And the GPUs need very high degrees of parallelism. Higher is better. And also the parallelism should be exploited in simile type or matrix production type operations. And also the preferable data layout exists. So application programmers should investigate new method, algorithms, and implementation method considering these four aspects. So this is my opinion for the question, the answer to the question, what should we do for the next generation applications. Okay. So, and finally, I would like to introduce my research work. And the topic is the sparse triangle solver. A sparse triangle solver is one of the important computational kernels, and it is often involved in the multi-grid solver or IC and ILU preconditioned iterative solver. But sparse triangle solver cannot be directly parallelized, and it needs some kind of things. And parallel ordering is one of the most popular methods for parallelization of the sparse triangle solver. And in 2000, 2012, so I proposed the algebraic block multicolor ordering method. And this method has been used in various applications because of its advantage in terms of convergence and the data locality and the number of synchronizations. And the method was used in these research activities published in the top conferences and the journals, especially for the high-performance implementation of the HPCG benchmarks. However, this block multicolor ordering method has a drawback in the implementation using SIMD vectorization, so not useful for the, for example, GPUs. And in this research, so we aimed to develop a new parallel ordering that has the same convergence rate as block multicolor ordering and makes the SIMD vectorization of substitutions possible. And this figure shows the quotient matrix generated from the application of the block multicolor ordering. So in each color, so you can see the diagonal block structure. And in this case, so we have 4 blocks, and the degree of parallelism is 4. And but this is, how to say, this is block diagonal structure, so it is not suitable for the SIMD vectorization. So then, we developed a new parallel ordering called HBMC, and I will show you some technical details. So first, we applied the block multicolor ordering to the quotient matrix, and then we applied the secondary reordering to the quotient matrix. And we gathered first unknowns in each block here, like that. And then, we gathered second unknowns in each block here. So in this case, how to say, we can get some good structure for the SIMD vectorization. And in this case, SIMD length is given by this size of level 2 block. So in this case, we could get the, how to say, this type of form of the coefficient matrix. And you can see the, this part. So this is diagonal matrices. So in this case, we can apply the SIMD vectorization to perform the forward and backward substitutions involved in the sparse triangle solver. So I'd like to show you some results. So these figures show the convergence behaviors of the relative residual norm. And 2 lines are duplicated, so you cannot see the difference. So, but it is correct. So HBMC new ordering exhibits the same convergence rate as the conventional block multicolor ordering technique. And this is a result on the KNL Geon5. And in this case, we can get the good result compared with the conventional BMC method. And today I would say I would like to show you the result on GPU. So this is a recent result on GPU, and blue bar shows the conventional block multicolor ordering, and orange bar shows the result of a new technique. So you can see the 15 to 40 improvement in the solver performance compared with the MC on the GPU. Okay. So I would like to move the summary slide. So I introduced the feasibility study activities of the application research group. So our group has 12 subgroups, and we investigated achievements expected in each application area around 2030. And each subgroup investigated the futures of the next generation computing system. And each subgroup also constructed a benchmark set that reflects the characteristics of the typical applications in each area. And for plan for 2024, maybe one is important thing, the modification of science roadmap following the architecture group's decision or report. And each subgroup will investigate new algorithms and implementation methods to fully utilize the next generation computing system. So in the personal opinion slide, so I think HPC workloads, AI workloads, AI for science are all important for the next generation computing systems. Thank you very much.